Yeah, fine.
Okay. So he's from the research group of Professor Frank Schreiber at University of Türingen, Institute of Applied Physics, Faculty of Sciences. He is a postdoc there, and he's also a project leader. And his expertise is in a variety of X-ray techniques and condensed matter physics. And this talk that he's giving is about this angular structure factor and hexatic phase in thick freestanding liquid crystal films. Okay, I just turn off my microphone and hand it over to you.
Yeah, thank you. Can you see my screen? I hope yes. So yeah, today I'm going to talk. Good. So thank you very much for giving me the opportunity to talk to you today. And I'm going to tell you a little bit about the liquid crystals and the peculiar hexatic phase which occurs in some of the liquid crystals. We study in our work so-called spectral liquid crystals, and usually they consist of elongated organic molecules. And those molecules at some not too high temperature, they form equidistant parallel layers, like shown on the left side of the slide. If you look, so in the perpendicular direction, so in the direction perpendicular to the layer surface, this looks like a periodic one-dimensional crystal. But if you look on the top, on the in-plane structure, the structure of a single layer, several situations can be possible. So at high temperature in the smectic A phase, which is very common for many liquid crystals and also for other systems, the structure within the layer is liquid-like. So it means that if you look on top on the smectic phase, you'll see something which resembles a two-dimensional liquid. So there is short-range positional order, there are short-range correlations between molecules, and there basically it looks very disordered, and the positions of the molecules are pretty random. If you cool down to some lower temperatures, of course, this two-dimensional crystal within each layer will freeze. And then the crystal E or crystal B phase can be formed. For example, here I show you hexagonal crystal E phase. Then, of course, like any crystal, it's characterized by long-range positional order and also long-range orientational order. And for some materials, for some liquid crystals, a peculiar phase occurs in between of those two. And this intermediate phase, which is called a hexatic phase. And if you look on the hexatic phase, it actually resembles a liquid. And the reason for this is because the positional correlations are still short range. So there is no long range order between the positions of the molecules. And therefore, this hexatic phase looks like a liquid. But on the closer look, you will notice that the bond orientation between molecules are ordered. So if you connect two neighboring molecules with a bond between those two molecules, so they reach a line connecting two centers of masses, you can see that those orientation of those bonds is preserved over large distances. So if you select a hexagon around of molecules surrounding a given molecule, and then you drew a similar hexagon somewhere away, even the distance between those two hexagons is pretty large, the orientation of those hexagons will be still the same. And this is called orientational order, and this orientational order is long range in the hexatic phase. So the hexatic phase combines two properties, so it's short range positional order from the liquid and long range orientational order from the crystal. And the hexatic phase occurs in some, like maybe 100 different types of different compounds of liquid crystals, but also it is pretty common in any two-dimensional systems. So for example, you can find the hexatic phase in colloidal particles on the surface of liquid, in superconducting vortices, in melting of two-dimensional crystal, in magnetic bubbles and garden films. So basically anywhere when you have the two-dimensional transition from between liquid and solid, you will see the hexatic phase. Or at least you have an opportunity to see the hexatic phase. And in two-dimensional case, the microscopic theory behind this transition was developed. And eventually in 2016, Nobel Prize was awarded to Taules and Kostelitz, who described the transition leading to the formation of the liquid of the hexatic phase in two-dimensional system. In our case, it's a little bit more complicated because in our case, we have a stack of layers. So our system is not truly two-dimensional. It's still three-dimensional. There's still interaction between the layers, and therefore the situation is a bit different, and there is no theoretical model which can describe it. So any information about the structure of the system is valuable, and it can potentially bring us to the understanding of what forces and what laws are governing this transition. So in our case, we were studying the three-dimensional stack of two-dimensional liquid crystal layers. And of course, we used X-ray diffraction to do this, because X-ray diffraction shows us perfectly the structure factor. And if you look at the structure factor from the symplectic phase, due to the absence of the orientational order in each layer, the structure factor, the structure factor will be uniform, so it looks like a ring. In the hexatic phase, due to coupling between the orientational order within different layers, and due to orientational order in between molecules, the structure factor, the uniform ring, splits into six hexagonal peaks. And therefore, by measuring diffraction, we can measure the structure factor. We can immediately see what phase we are working with. So we performed our experiment at P10 beamline and DAISY. And this is a scheme of our experiment. So we prepared a freestanding liquid crystal film with the layers parallel to the surface. And then we use focused X-ray beam to measure the diffraction in the transmission regime. And the detector was placed right behind the crystal, so we can nicely see the diffraction pattern formed by X-rays scattering from the molecules. And there are some parameters of our experiment. And basically, we were changing the temperature. And we were going from higher temperature, from symplectic phase, to the lower temperature hexatic phase, and observing how the diffraction pattern will change, and try to understand what's going on in real space. So these are 4 liquid crystal compounds we studied. So you can see that all of them are elongated organic molecules, and all of them have a symplectic A to hexatic B transition somewhere between 60 and 100 degrees Celsius. So we always work at slightly elevated temperatures. It was pretty convenient because you just need to heat up your material a little bit, and then you can change the heating to change the temperature. And this is experimental result. So this is one of the material measured in symplectic A phase. You can see the uniform ring corresponding to the absence of the orientational order. And if you cool down the same material, you can see that this ring splits into 6 hexagonal diffraction peaks. This is a manifestation of the bond orientational order. And of course, we were not only interested in observing this transition, but also we wanted to describe the structure of the hexatic phase and structure of the symplectic phase. So we wanted to understand what are the correlation lengths and what are other microscopic parameters that can describe this phase. So to study the positional order, what we did the radial scan through the peak, through the ring, or through the diffraction peak in the hexatic phase. And it's shown here on the picture in the lower part of the slide. And it happens that at all temperatures, the radial scan can be well described by the Lorentzian function. So this is a Lorentzian function. And then 2 parameters can be extracted. First of all is the radius of this ring, which corresponds to the distance between molecules. And second, which is more important to us, is the width of this peak in radial direction. And this peak is inversely proportional to the positional correlation length. So by measuring the width of the peak, we can say, we can establish how fast the correlations between the molecules decay. And this is the temperature dependence of the positional correlation lengths for all 4 compounds. So at symplectic phase, at above the transition temperature, it's pretty small. So just few nanometers, meaning that the positional correlations are lost within a few molecules, which is typical for liquid. But in the hexatic phase, the positional correlation length becomes pretty large, but it still is a short range order. So the still correlations decay exponentially. So even that the quantitatively, the positional correlation length is pretty large, the order is still short range. And in the same manner, what we can do, we can also look at the at the azimuthal scan through diffraction peak. So we're doing also azimuthal scans of the peak. On the right-hand side, you can see the results. So general tendency for all compounds is that the peak is very broad and not very intense at high temperatures close to the phase transition. But when we go deeper to the hexatic phase, the peaks becomes narrower and it becomes more intense for all 4 compounds. And more strikingly, more interesting is actually at all temperatures and all compounds, we found that it can be described by the Voigt function. So for those who don't know, Voigt function is convolution of the Gaussian Lorentzian functions. So it is shown in the left part of the slide. And it was, no one ever did many predictions about the structure, about the shape of the hexatic peak. And he was very surprised to see that actually the Voigt function is a very good approximation for the azimuthal profile of the hexatic peak at all temperatures. And here I show you some results at given temperatures for different compounds. You can see that always the Voigt function, which is shown with a purple color, bluish color, fits the diffraction profile much better than Gaussian Lorentzian function. And the reason for this is not just because the Voigt function has a little bit more parameters than the usual Lorentzian or Gaussian peaks, but the reason lies in the structure of the hexatic phase. So the Gaussian counterpart from the Voigt function actually comes from the fluctuations of the bond rotational order parameter. So as in any system at any given temperature, the orientation of the bond of the bonds between the molecules fluctuates a little bit. And those fluctuations can be described in the Gaussian model, and therefore we have the Gaussian contribution to the Voigt function. But since the orientational order coupled with the positional order, and the positional order in hexatic phase is still short range, we have some short range contribution to the orientational order, and we have the Lorentzian contribution to the rotational order. So the Lorentzian contribution can be described by the parameter kappa, and this kappa originates in the short range positional order and the coupling between the positional order and the orientational order. And those two contributions give us the Voigt profile of a hexatic peak. First, it was described by the seminal work of Epley and Brinsma in 1984. And if you look in this work, you can actually see that what they did. They wrote the very general equation for the structure factor that is shown here, and it comes from the equipartition theorem. And then for normal liquid without bond rotational order, it will just have some term A in the denominator. But because there is because the orientational order is present in this system, this orientational order is covered by the positional order, we have the additional term F in the denominator, and this additional term has 3 contributions purely from the density fluctuation, so purely from the positional order, from the pure orientational order and the coupling between them. And that what they did, they considered very general they treated in very general way those equations and showed that indeed the azimuthal profile can be of the hexatic structure factor can be represented at a Voigt function. And this was pure theoretical work. And now finally we were able to perform experiment and show that yes, this is indeed true. The Voigt function gives a better approximation, and not only for one compound, not only at a specific temperature range, but for all studied compounds, and we studied 4 of them, and for all range of existence of the hexatic phase. And we even could go a little bit further. So there's 2 parameters, both of them originating from the positional order. So the first one is the positional correlation length, so which we can find from the radial scan of the diffraction pattern. And the second one, kappa, is somehow related to the coupling between the position and the bond orientational order, and it can be determined by fitting the azimuthal profile with the Voigt function. And since both of them originate from the positional order, the question is, are they correlated? Or in other words, is the ratio between them somehow a constant, or how it changes? And we used our data to plot this ratio. So here I show you the dimensionless ratio between gamma and kappa as a function of temperature for all 4 different compounds. And you can see that actually, of course, it's not strictly constant, but the values are pretty close to each other for different temperatures for different compounds. Because in theory, this ratio can be from 0 to very large values. And you can see that for all compounds, if you move a little bit away from the phase transition points to the deeper hexatic phase, you can see that the value lies somewhere between 0.2 and 0.8. So it has some uniform, some universal value for all compounds, and this gives us hope that probably all the interactions in different molecules are still governed by the same physics, and this value of this dimensionless ratio can be explained or can give us some insight in the structure of the hexatic phase. So in the end, I would like to summarize shortly what we've done. So we studied 4 different compounds, and we found that the angular shape of the diffraction peak is described by the Voigt function, which is a convolution of the Lorentzian Gaussian function. And we have actually explanation why the Voigt function works. So the Gaussian contribution comes from the fluctuations of the phase of the bond orientation order parameter, and the Lorentzian contribution arises from the coupling between the short-range positional order and the long-range bond orientation order. And these results are in a good agreement with the previous theoretical works. And if you're interested, we just have published the paper in SoftPate when we show all the results, and actually also some more of them together with the theoretical background I talked about. So with this, I would like to thank you for your attention and also thank all the collaborators we worked with to make this work possible. Thank you.
Okay, so thank you very much for this talk. Do we have any questions?